Good evening all. Welcome to week 4 of the live session for Fundamentals of Convective Heat Transfer course. So this week we will be discussing, like in the last week discussed on glacier solution and Paul Hausen solution for constant wall temperature, and we also discussed on constant heat flux as well. And then further we also discussed something called Falkner-Stan solutions where the U infinity is not constant. And in this week we will discuss another technique to solve the same kind of problems, and this is called an integral method. Like unlike the previous one where differential volume is considered, here we'll solve for some mean quantities. So we have similar to the momentum equation, here we have momentum integral equation, and instead of energy equation we'll be having energy integral equation. So I'll be not going through the complete derivation because as it's already covered in the lecture video, so we'll focus more on the problems. But maybe for the first half an hour or so, I'll give a quick summary of these techniques. So to those of you who have not already gone through the lecture videos, it will be a little useful. Okay, people are still joining. We'll wait for a couple of minutes for a few more students to join, and then we'll get started. I think we can get started. First, we'll get started with the momentum integral equations. So the idea behind this is we have something called integral formulation, where the previous derivations that are differential in the sense they for a small control volume, here we'll consider a bigger control volume, and we'll not worry about how the things are varying inside kind of in a continuous sense, but then we'll be only worried about the mean quantities, like we need the mean momentum getting conserved and the total energy getting conserved. So the main idea here is we have one equation. So for example, when we are solving the momentum integral equation, it's just one equation. So I can have at most one variable, otherwise I will not be able to solve it. So at max we can have one variable for each equation. So if you have momentum integral, if you use one momentum integral equation, we can solve for one variable here. So that will be the hydrodynamic boundary layer thickness. And using the energy integral equation, we'll solve for the second variable, which is the thermal boundary layer thickness. So these will be the two variable, two unknown problems, two equation problem that we'll be solving. So we'll start with the momentum integral equations. We start with the same boundary layer equations that we have before, the continuity, the momentum, and the energy equations. So the integration we are doing from 0 to delta, like within the boundary layer we're integrating, and we are assuming that at delta, the velocity has reached the free stream velocity unit. So this is the forced convection problem. So if you do the integration, a little bit of mathematical steps here, which I'm kind of skipping. But the main ideas are you take step by step, integrate this, use the by parts to get a corresponding term for each one of them. But then when you try to do integration by parts, you will be left with the unknown value b, which is obtained by doing an integral for the continuity equation, which we'll do in the next slide. So when you do the integration for the continuity equation, we'll be able to find v delta. V delta is basically the velocity, the vertical velocity component at this point. the vertical velocity component at this point. Once we know that, we can substitute that back and we can obtain the LHS equation as follows. But this LHS equation is again an integral formulation, so we would like to take this derivative of x outside. So when you do that using the Leibniz integral rule, so this is the final equation we'll be left with. See, on the RHS, we just have nu del square u del y square, which basically translates to giving me tau w by rho. So if I equate LHS and RHS, take the u infinite outside, because here we have a flat plate, u infinite or the free stream velocity is not a function of x. So I will be able to take it outside the ddx, outside the derivative, and this is what we will have. So now once we have that, so the shear stress is given by wall shear stress is given by rho infinity square times ddx of this particular quantity. If you recollect, this is something we defined in week 2 lecture, or in week 3, sorry, in the last week lecture itself. This is something we call the momentum thickness, if you recollect correctly. So this can also be written as rho infinity square times theta, or maybe I'll use a different notation because theta will be using for temperature. I'll write it as delta star star. The delta star star is momentum thickness. Or to put very simply, how we define momentum thickness is basically rho infinity square times delta double star is the momentum deficit that is happening across the boundary layer from the leading edge to that particular point where we have considered. That is how we define the momentum thickness in the last week lectures. So now what we are saying from this whole equation is that the rate of shear stress, like basically the amount of force you are exerting the shear stress, should be equal to rho infinity square times delta star, which means whatever momentum deficit is happening within the boundary layer is happening because of the shear stress. That's the kind of an intuitive statement to understand this particular equation. Now the problem now reduces to finding this particular velocity profile, and eventually from there get the tau w. If I know u by infinity, I'll be able to find tau w. But as I said before, this is just one equation, so we'll be able to solve for at max one variable. So what we will do now is we'll try to express this u by u infinity and tau w, both of them, as a function of delta and solve for delta. Like if you write u by infinity as a function of delta and tau w as a function of delta, because we already know tau w is minus nu times nu times du by d infinity, which we already know. So if I assume the u as a function of y, and then I'll substitute that in this integral, then I'll get an equation for delta, and then I'll solve for delta. Once I get delta, I'll be able to calculate my u and tau w from there. That is the whole idea in this integral methods. As is mentioned in the lecture videos also, the question of choice, how do we choose this particular profile, and let's say if I choose one particular profile, if I want to increase accuracy, what should we do? And these kinds of questions cannot be answered with this particular method. So this is again an approximate method. So you choose a particular profile and you see whether it fits or not. If it doesn't fit, we cannot do anything to improve it. Like we choose a different profile, no other option. So now we have, let's say we'll take a cubic profile. Why cubic profile? Again, this depends on how many constants you can determine. In general, you take any power law equation, like any power series. The problem is, how do we obtain the coefficients of this? Because we don't want these coefficients also to be unknowns in this equation, because in this we can have at most one unknown variable. So what we try to do now, we just use the boundary conditions. So the boundary conditions are, we know at the wall, the velocity has to be 0. At delta, the velocity has to be u infinite. And we also have at delta, the shear stress should be 0 because the velocity has reached the free stream and then it is not changing further. So du dy at y equal to delta should be 0. And these are three conditions. So I'll be able to find three constants from this. But we have one more constant. So in order to do that, we'll take at y equal to 0, we'll take the governing equation. We know that u and v are 0 because it is a flat plate. There is no v component or u component. Like on the surface of the wall, the no slip condition will ensure both of these velocities are 0, which will give us that d square u by dy square should also be equal to 0. So now we have 4 conditions and 4 unknown variables. So we'll be able to find all these constants using these 4 boundary conditions. That's a little bit of algebra here that I think you'll be able to do. Once you substitute and solve for the equations, this is the final equation I'm getting. U by u infinity is 3 by 2 times y by delta minus half y by delta cube. So at y equal to 0, this will be 0, and y equal to delta, this will be equal to 1. So once I have u by u infinity as a function of this, I can substitute this back into the momentum integral equation that I have taken before. So if I substitute this equation and then do the integration, so this is the term that I would be getting. Similarly, I will do on the LHS side. I know tau w is mu times du dy at y equal to 0. Again, we know u as a function of infinite and y by delta. So we can substitute that and get another equation. So LHS equal to RHS, which we substitute, and if you do the integration, you'll get an expression for delta. If you recollect, when we are solving this using Blaze's equation, we were getting something like 5.2 here. So now instead of 5.2, we have a different value, 4.64. But the scaling again works. Delta by x is proportional to Rx to the power minus half. This method is so the two things that you need to remember here are if you remember this equation, which again, as I said, straightforward, the amount of force that you are exerting in the non-dimensional sense should be equal to this is your momentum thickness. That is basically the momentum deficit that you are going to have across the boundary layer. You equate both of them, and then you will take again. This equation is valid only for flat plate because we are assuming u infinity square is constant and we have taken it outside the derivative. But in general, if you remember when we solve the problem in say Faulkner-Scan equations, in that u infinity is not constant. U infinity is cx to the power m. Then you will have the derivative with respect to u infinity also. So you cannot take it outside. Then you would have to solve like you can still use the same technique, but then it will have a little more involved mathematics. Now that I have delta, the next step is to calculate the shear stress, which is again straightforward. So we'll take CFX as tau w by half rho infinity square, where tau w is, which we already calculated before, 3 by 2 mu infinity by delta. So if you substitute these equations and then a little bit of rearrangement will give me this skin friction coefficient as 0.646 by Rx to the power half. So these values are quite close to each other, like within 2.7%. So last week we did so many transformations. We used some assumptions that it has to be similar. The same assumption is something that we used even here. So if you recollect, here we are writing again u by infinity is a function of y by delta alone, where delta could be a function of x. So this is again something like the self-similarity assumptions that we have used before. Are there any questions up until here? Okay, if there are no questions, now that we have found out what the hydrodynamic boundary layer thickness and the skin friction coefficient, the next step is to kind of extend this particular method for a constant wall temperature case. Here we'll consider the same problem, but then we are assuming that delta is greater than delta t. When is this true? Again, we are also assuming that there is an unheated portion x0 where only the hydrodynamic layer will be there, and from here the thermal boundary layer will start to form. The same steps will follow. We'll again integrate from 0 to delta. Now, previously we have integrated from 0 to delta, but now we'll be integrating from 0 to delta t. This is again because we are only worried in this integral, because beyond this integral what happens? If I go anything beyond this integral, the temperature is constant. So delta del y will become delta del y, delta del square, t del y square. All of these quantities will become 0. So there is no point in integrating beyond delta t. So we'll only integrate up to delta t. We use the same equations that we derived before. The only difference here is previously we have v delta, now we'll be having everything in terms of delta t. The RHS is straightforward again, minus alpha delta del y. So this can be written as qw prime by rho cp. So a little bit of rearrangement will leave me with this equation. Again, we will use the Leibniz integral rule to take the derivative outside. If you have the derivative outside, you will eventually left with this equation. This is also very similar to the equation that we have obtained for the momentum integral. Like here there was tau w, now instead of you have q all, and in previously it was u minus u infinity, like 1 minus u infinity, u by u infinity. Here now we have t minus u infinity. So again, we'll follow the same approach. We'll assume a cubic profile. The boundary conditions are also similar. At y equal to 0, it will be wall temperature. Y equal to delta t, it will be free stream temperature. Derivative should be 0 at the delta del y should be 0 at y equal to delta, and at y equal to 0, del square t del y square should be 0. This is again from the governing equation. We can obtain this result. Little bit of algebra will leave you with this particular equation, with this particular result, which is again, this profile is very similar to u by u infinity. At y equal to 0, it will be 0 because t minus tw is 0, and y equal to delta, this will be t infinite and this will be equal to 1, which you can obtain by substituting that value here, y equal to delta t. So we'll use the previous solution of u by u infinity and delta x, and t, the one that we got now, t minus tw by t infinity minus tw, into the energy integral equation. And again, a little bit of algebra will eventually leave you with this term. The most important assumption now here is we will assume that delta t by delta for Prandtl number greater than 1, this particular quantity will be very less than 1. So in that case, then when you compare this square versus the fourth order term, like if particular number is less than 1, then as you increase the power of it, that number becomes diminishing, like very small. So if you have epsilon less than 1, then epsilon square will obviously be greater than epsilon power 4. Like take example, say 0.1, epsilon to be 0.1, then epsilon square is 10 power minus 2, and this is 10 power minus 4. So this is way higher than this particular quantity, so you can neglect the other term. So we'll be neglecting this term, and then we'll solve only with this, with the first term. And if you solve that equation, these are a little bit of algebra, which I'm excluding for now, which I'm skipping now, which you can go through at your time later. I'll upload all of these, and anyway, the lecture videos are also there. Slides are also shared with you, so you can do it at your do it later. The only thing that we have now is we'll be solving an ODE, which means we would require the boundary condition. So the boundary condition is what happens at x equal to 0 or x equal to x naught. As we define that x naught is the length where it is unheated. So that is where the thermal boundary layer will start to form. So at that particular point, x equal to x naught, we have delta T should be 0. That is the boundary condition we'll be using. When you substitute that condition, we'll be left with this particular equation. When x equal to x naught, this will be 0, and otherwise this particular delta T will vary as delta T by x will vary as Prandtl to the power minus 3 and RH to the power minus half. So once I obtain the value of delta T, the next thing is calculate local heat transfer coefficient, Nusselt number, heat flux, etc. We can calculate from this. So the heat transfer coefficient is minus k delta del y. This is basically the q double prime by tw minus t infinite. So that this will give me 3 by 2 k by delta t. Delta t is something that I already know from here if I substitute that back. So this is the equation I'm getting. Again, if the x naught is 0, basically there is no unheated length, then you can substitute x naught equal to 0, and that will give me this equation, which is very close to the equation that we obtained using the Paulhaussen solution as well. Like error is within 2.4%. Obviously, the next question is, we have assumed here that in this particular step, we have assumed the Prandtl number to be greater than 1. So the natural question is, what happens if Prandtl number is less than 1? So what you have to do is, when Prandtl number is less than 1, then you would take the other term. So instead of this term would go to 0. Sorry, this term would go. This term will be neglected instead of the other term, and then you will be able to solve. Once you solve that, the resulting equation will be something like this. The most important aspect here is the relation that you get here has Prandtl to the power half, while the previous relation has Prandtl to the power 1 by 3. We'll also solve a problem on this, a specific case where Prandtl number is very much less than 1. Like for say liquid metals or something which have very high thermal conductivity, where Prandtl number will be very much less than 1. We will solve for that case, and we will see whether this Prandtl number to the power 1 by 2 is something that we actually get. The next case of scenario is the uniform heat flux condition. So here again we'll use the same integral equation. The only difference is, previously we were able to define that Tw is constant. Now because Tw is not constant, it could actually be a function of x. So the problem boils down to identifying what is that function. So can one of you recollect how the function will look like? We've discussed this even when we are solving the Paulhaussen equation. What should be the functional form of Tw? I think this is also there in one of your assignment problems, and we discussed this in Paulhausen solution as well. Yeah, so it should be something like square root of x to the power 1 by 2. If you recollect, we were solving this as equal to some lambda, and we were finding that lambda, right? Lambda equal to half will give us constant heat flux. I think you'll be able to recollect. You can, if not, then please review the last two lecture videos as well. So now we'll assume that all these constants are again functions of x, which are yet to be found out. Again, we'll use the same boundary conditions that we have before. The only difference now is previously at y equal to 0, we told T equal to Tw, but now we will be having the heat flux minus K del T by del Y equal to Qw. So now C1 instead of being equal to Tw will now C0 instead of being equal to Tw, now we'll get in terms of C1, which is minus Qw prime by K. The remaining are the same. So if you substitute that, the profile will be something like this. T of xy is T infinite plus this particular quantity here, where you have delta T, which is a function of x, which we do not know as of now, which is something that we'll be finding out. So the Tw of x is basically substitute y equal to 0, and you'll be getting Tw of x, which is T infinite plus this particular quantity. So this particular quantity is the one that we'll be trying to find out. So if you recollect, previously we were writing it as Tw of x is T infinity plus some constant times x to the power m, where x to the power lambda, where lambda is your half or something. Which you do not know as of now. So we'll try to find this one delta. So the process remains the same. So now you have this equation, you have to substitute in this integral, take the and then get in terms of d delta t dx, this qw prime. So if you substitute that here and again take the same assumption that Prandtl number greater than 1, so delta t by delta is very much less than 1, so this term can be neglected. If you substitute that, this is equation for delta t in term and delta t. So this is the equation I will be left for delta t by x. Once I know delta t, then I can calculate the corresponding Tw of x, which turns out to be this. So here you can see again, here you will have an x to the power half, and here you will have x. So this will be of the order x to the power half, right? Like for x not equal to 0, this term will go off. So here you have an x, and here you have x to the power half. So this will be square root of x. That is what we got even when we were solving the Paulhausen equation for a constant heat flux case. Now that I have the values of Tw in this, I can directly calculate the Nusselt number. So this is the correlation we have, and this is kind of within 8% as we compare with the Paulhausen solution. Are there any questions up until now? Yeah, I guess there are no questions. So this is the one that I was telling you about. So you can solve like this, and then you'll get the same as before. So in summary, what we have discussed in this particular lecture videos are basically on using the integral technique to solve the boundary layer equations. Basically, we'll solve for the momentum equation and then the energy integral equation. So each equation we can have only one variable. So using the momentum integral equation, we will first find the hydrodynamic boundary layer thickness, and then we will use the energy integral equation. Depending on the case whether Prandtl number is greater than or less than 1, you will be solving for the thermal boundary layer thickness. Once I have both the boundary layer thicknesses, I can calculate the shear stress and the heat transfer. The only thing is these are not exact solutions, these are approximate solutions. So we have to assume a profile for the velocity and temperature, and for that particular profile we'll get values of Nusselt number, spin friction coefficient. Again, all these values will be for that particular profile. So to put equations together in one place, so this is the momentum integral equation. To remember it easily, you can think of it as the momentum deficit the momentum deficit, which is rho u infinity square times delta double star, which is the momentum thickness, is balanced by the shear force. This is the momentum integral equation. Similarly, you can think of this also as some kind of a deficit, energy deficit, which is balanced with the heat flux. Sorry, energy excess that is added to the boundary layer because of the external heat flux. And the delta will be given by 4.64 instead of 5.2, and CFX is 0.646 instead of 632. Similarly, for the energy integral equation, we have two different cases. We either have delta T by delta less than 1. So this is basically for Prandtl number greater than 1. And for Prandtl number greater than 1 is what these two equations are. Again, we have two different kinds of boundary conditions. Either you can have a constant wall temperature or a constant heat flux. For constant wall temperature, this is the correlation for Nusselt temper, and for constant heat flux, there will be another correlation. Both of these correlations are for the case when Prandtl number is greater than 1. And the corresponding wall temperature profiles. This is the profile you assumed in case of constant wall, and in case of constant heat flux, TW of x is given by this. Again, you have the same equation as before. The other equation, I'll just put it in the same place. This will be by T of xy. Yeah. Yeah, I think that kind of summarizes the important equations for this particular session. So, are there any questions up until now? Yeah. Okay, if there are no questions, then we'll get started with some problems. Some problems have already been discussed in the lecture videos. So I would like you to solve these problems on your own, and then we'll have a discussion on how to go about solving them. So this is the first problem. Please go through it. It's again the same like the one that we discussed. So you have a flat plate. The initial certain length up to 25 centimeters is adiabatic. Again, then you have a heated surface, and then again you have an adiabatic. It's like you have a flat surface and you have put a heater in certain portion of the flat surface. Now air at 20 degrees Celsius and 1 atmosphere flows over the plate at 6 meter per second. So air is coming at 20 Celsius, 6 meter per second. Maybe I'll put it. The plate has both unheated surfaces. If this particular surface, heated surface, whatever we are having, is maintained at a constant temperature of 140 degrees Celsius, calculate the total heat transfer rate. Are there any ambiguities in the question or anything that you did not understand? Yeah, I guess the question is clear. So maybe I'll wait for say 5 to 10 minutes so you'll be able to answer it. I'll wait for a couple of minutes. Before trying to solve the problem, just see whether all the information is given to you that is required to be able to solve the problem. If not, just let me know. So what's the plan to go about solve this problem? So we are asked to find the heat transfer rate. So I need to know the Nusselt number. If I know Nusselt number, then I'll be able to calculate that. In order to calculate the Nusselt number, I need to know the Prandtl number and Reynolds number and the corresponding correlation. So I need to decide which correlation to use. Now we have so many correlations now. I have to decide which correlation to use. So basically the steps are like this. So it goes in a reverse way. So you need the total heat transfer rate, for which you need to calculate the Nusselt number, for which you need to know whether the particular equations that we have derived up until now are valid for this particular problem or not. So in general, you have to first check whether you are in the laminar condition or not, laminar boundary layer condition scenario or not. If you are not in the laminar case, and none of these whatever we have discussed up until now are useful in any way. If turbulence is there, then the correlations are completely changed. So first you have to check whether in your laminar design, and in order to check that, you need to calculate, say, which number would you calculate in this case to decide whether you're laminar or not. Yeah, Reynolds number is something that you have to calculate. And in order to calculate Reynolds number, you need to know the properties. But now I have two different temperatures here, air at 20 degrees Celsius, and then close to the wall it will be 140. So I have multiple temperatures here. So now I have to evaluate the properties at some kind of temperature, some kind of other temperature which is neither 20 nor 140, which we have discussed in the last week as well. That is called the film temperature. So all the properties for calculating this Reynolds number or any other non-emission number that you will be using will be calculated at a film temperature, which is defined in a different ways depending on the problem that you are solving. In this case, first you have to find that film temperature, then evaluate the properties, and then see whether you are in the laminar regime or not. If you are in the laminar regime, then you have to decide which correlation to use for Nusselt number. It is a constant temperature, but still there are other cases even within the constant temperature case. If the delta T by delta is less than 1, we have one correlation. If it is greater than 1, then we cannot use that particular correlation. We have to check whether that particular criteria is satisfied or not, and if that is satisfied, then we have the Nusselt number that is derived previously that you can use. Then you have then the question asks you to find the total heat transfer rate. This Nusselt number will only give you the local heat transfer rate. So then you have to integrate it over the total plate length. Integration should be done from 25 to 75, because this is the only reason where the constant wall temperature is maintained. So in this temperature you have to integrate, and then you will get the total heat transfer rate. Okay, we'll go step by step. So first step is to compute the film temperature, which is basically the mean temperature of TW and T infrared, which both the values are given. So that will give me 80 degrees Celsius. The properties, I'm giving you directly the values. So at 80 degrees Celsius, these are the values that you can take. You can just note them down. So with these values, if you compute the Reynolds number, where should I compute the Reynolds number? Yes, the Reynolds number keeps increasing as you go along the length of the plate. So I'll be calculating Reynolds number at the edge of the plate, right? So what length should I use for Reynolds number at the edge of the plate? Should I use 50 centimeters or 25 plus 50? Yeah, I have written the answer here, so you'll be saying, but why is that particular one chosen and not the other one? Yeah, right. So the hydrodynamic boundary layer is starting from this point. So the coordinate system, the origin for the hydrodynamic boundary layer will start at this point. So we'll be using that x value. So x will be the 0.75. So the Reynolds number will be correspond to that particular x, velocity times x, that particular length divided by the kinematic viscosity, which is giving me around 2.15 into 10 power 5. For a flat plate, the critical number for transition is 5 into 10 power 5. So since it is less than that particular value, you can consider this as a laminar, which means the theory that we have developed, like even the Blaze's solution or the integral theory that whatever we have discussed in today's session, like just a few minutes before, that can be used. Now that we know that that can be used, the next question is we need to decide the appropriate criteria. So that criteria, again, we have two different correlations. We know that if for delta T by delta less than 1, we have one correlation, and for greater than 1, we have another correlation. So we need to decide what is the value of delta T by delta. So I know delta T expression in terms of x, I know delta expression in terms of x. I can substitute delta T by delta. So this is the equation I'll be getting. X naught is something that I already know. The X naught is 25 centimeters and X is 0.75. So if I substitute that, I'm getting around 0.903. You can just calculate and confirm if you are also getting the same answer. Yeah. And this value is less than 1. So the correlation I should be using is this one, right? So I'll choose this correlation. Once I've chosen, all that is required is you have to just calculate it, calculate the integral of this particular expression. Like only then I'll get the total heat transfer rate. So first I'll derive hx, which is Nusselt number times k by x. And then qw is basically h bar times this value. H bar is integral. Integral should be from this point to this point, which is from 0.25 to 0.75 times hx dx. So if I substitute the values and integrate, I'm getting it around 11.13. We'll wait for a couple of minutes so you can do the integration and confirm me if you're also getting the same answer. Just see that I have reversed this, like so that I can write it in terms of x and put it in my calculator. This will be x by x naught, so I've changed the power here. You can quickly calculate and tell me if you're also getting the same answer. Yeah, you're also getting the same. Fine. So now we have the mean heat transfer coefficient. All I have to do is substitute in this equation. So I know the h bar value, I know TWT infinity. What is the value of A? Area, what area should I consider? Yeah, the heater area, which is 50 centimeter times the width of the plate, which is in the other direction, in the third direction, that is 30 centimeter. So if I substitute those values, 11.13 into 0.5 times 0.3 times the delta T is 140 minus 20, that is giving me around 200.34 watts. Yeah. So the methodology is clear, right? So the steps are as follows. So you are required to find the heat transfer from particular surface, which is like a flat surface. So first thing you observe that it is a flat surface, and then there is no external pressure gradient, which means that free stream velocity is constant. Then we can use the flat plate as a flat plate theory that we have developed until now. The next step is whether to know whether it is laminar or turbulent. So for which we calculated the film temperature and all the properties at the film temperature, determine the Reynolds number, and check whether the Reynolds number is less than the critical Reynolds number. Because it is less than that, we decided that it is a laminar flow. And then we identified that, okay, from integral solution, we have two different cases, two different correlations for two different scenarios, depending on whether delta T by delta is less than or greater than 1. We already know the correlation for delta T by delta. So we substitute the values there and then determine that this value is less than 1. And that is because of the length of that depends on the heated length. So if this heated length had been a little higher, so let's say if it is instead of 50, if it is a 100 centimeter or something, then my delta D by delta would be different. It could be greater than 1. Then I would have to go switch to a different correlation. So if you are integrating from, say, if it is 100 centimeters, so there is a particular point after which delta T by delta might be greater than 1, and here delta T by delta is less than 1. So up until that particular region, so then you will be having two different regions. In the first region, you have to use the first correlation, and for the second region, you have to use the different correlation. How to do that is something that we have not covered up until now in this lecture videos as well. If you're interested, you can go through the reference books that have been that have been given in the lecture videos. You can go through, say, the convective heat transfer book by Kakak or any other page, and it was not mentioned, but in Kakak these problems are actually mentioned. Actually, there is an example problem which helps you solve that kind of scenarios where the correlations will actually change as you switch from into different regions of the plate. But luckily in this problem it doesn't happen. So it is only 50 centimeters, so delta T by delta is less than 1, so we can use the correlation directly. And that correlation will only give me the local heat transfer. So now what I have to do is integrate it over the total length. As I do the integration, I'll get the total heat transfer. I'll get the total average heat flux, sorry, average heat transfer coefficient, and then multiply with the total area times W minus T infinity, which will give me the net heat transfer rate. Are there any questions in this problem? Good. I guess there are no questions. We'll move on to the next problem then. This is again a kind of some standard problems that you have. So consider a steady 2D laminar boundary layer flow of a very low Prandtl number fluid. This is the most important one that I like to highlight here. So when I say very low, it's basically Prandtl number is very much less than 1. Of constant thermophysical properties with a constant and uniform free stream velocity U infinity and temperature T infinity. If the plate is isothermal at TW, and we are assuming the profile, like I said, in all this integral thing, we have to assume some particular profile, and we are assuming it to be A plus B sin C1. Assuming this profile, solve the energy integral equation that you already have, and then determine the value of delta T by X. How is it different from the one that we derived, like say half an hour before? We have derived, we have solved the energy equation. Yeah, there are two key differences. The first one is we said explicitly that it has a very low Prandtl number, whereas in the previous derivation we have used that delta T is less than delta, which means Prandtl number is greater than 1. Yeah, that is one difference. In the other one, yes. So the other one is the temperature. We have assumed a cubic profile. Now we are assuming some other profile here. But the difference is not in the type of profile we are assuming, but as such. But the key difference that you have to identify now is previously when we are assuming a cubic profile, we have four unknown constants that we need to be determined. However, now we have only three constants. So which means one of the boundary conditions that we were using before cannot be used in this particular problem. Yeah, I would like you to ponder over that. And yeah, maybe I'll wait for a couple of minutes so you can attempt to solve it, or just propose for the way that you're going to solve it, and then we'll discuss how to go about that. Yeah. So how do you go about this? So first step is to identify the values of ABC. Yeah, that is what I was saying before. So now we have only three constants. So the boundary conditions, again, if you start with say these boundary conditions. So the condition that I have left here is the delta del y, yes, at y equal to delta t should be 0. But that is the most important condition. But let's say if you started with these conditions, what would happen? So if I started with this condition and try to solve these equations, yeah, so I'll have from the first one a equal to tw, and from the second one I'll have b to c, like one of them has to be 0. But if I substitute that in the third equation, then I'll not be able to solve for this particular problem, which means that for this particular case, one of the boundary conditions cannot be used directly, and that has so we'll resort to the other condition. So we will choose delta del y at y equal to delta to be 0, and this has to be true. So if you substitute that, then we'll have c is pi by 2 delta t and b equal to t infinity minus tw. So now I have my equation for t as tw plus t infinity minus tw times sine pi y by 2 delta t. So I can get the equation for theta from this. Now I have to solve the energy integral equation. The question now is, what is the velocity profile that you will use here? So I need to find u, but what will be the velocity profile that I have to use here? Okay, you want to try the cubic profile? Okay. Yeah, but the most important thing that we have left out here is something called very low Prandtl number. So what happens when the Prandtl number is very less? Yes, your thermal boundary layer thickness compared to the hydrodynamic boundary layer thickness will be very high. So delta T will be very high compared to delta. So if Prandtl number is very low, so which means the velocity will have, so if you check the velocity profile here, so the velocity gradient will be small, and for most of the region it will be constant. This is how the velocity profile looks. So what we are going to assume now is this region here is very small because Prandtl number is very much less than 1 compared to the total region. So we will assume that u equal to infinite, even u equal to u infinite, even within the thermal boundary layer thickness. So this is a simplification that we are going to get when the Prandtl number is very much less than 1, right? So that simplifies our problem. So you don't have to assume the cubic profile, you will assume a constant velocity profile. Now with constant velocity profile, this will be u equal to infinite, then you will be able to directly solve. Like it will be very simple. So you can do the integration, substitute that value, and then if you perform the integration, this is the equation I will be getting. So this is the minus alpha del t del y term, and this is RHS term. So if you substitute that and do the integration, I'm getting something like this. So this is just the integral terms. So if I take this on the other side, so I have a dx term. So if I integrate this to dx, and this will be delta t square by 2. So from this, I'm getting delta t by x as 4.16 times Prandtl to the power half RH to the power half. So you can see the difference of this with the previous equation that we have. So this, the numerator was also more or less close to the same that we have obtained as before. If you see the previous one, see the numerator is more or less the same. So but the key difference is in the value of the exponent for Prandtl number. So in case of Prandtl number greater than 1, we have this as exponent in terms of 1 by 3, while when we have a very low Prandtl number, then this is exponent to the power 1 by 2. That's the only difference that we have from the previous case. Now let's do the same problem, but now determine the local Nusselt number. This should be straightforward now, right? If you know delta t by x, how do I go about calculating the local Nusselt number? Yeah. So all you have to do is we have delta t by x. So Nusselt number is defined as minus delta del y at y equal to 0. So this is basically my hx by this quantity is h by k. This h times this is basically q, so this is k times this q, so this is h by k times x, and we already know del t by del y as this particular quantity which we have obtained just a little time before. So if you substitute those values, I'm getting the equation as this, which is again, if you remember, this is also very close. Like previously it was 0.331 times Prandtl to the power 1 by 3, but now it is 1 by 2. So that is the most important thing that I want you to notice in this particular problem. When you have a very low Prandtl number, the exponent for the exponent in the Nusselt number expression will change from 1 by 3 to 1 by 2. Okay, and this we have obtained again for this kind of profile and not with a cubic profile. So if you have used a cubic profile, then you will get a different expression for this. This is just kind of simplified. Like if you use this profile, then one exponent is gone and your integration also becomes a little easier. So I've taken this profile as an example problem, so you can understand the main scaling arguments that we discussed in a couple of weeks before. In week 2, we discussed something called scaling argument. Even there, we obtained the same result. We obtained that for very low Prandtl number, the exponent should be 1 by 2 and not 1 by 3. You can revise week 2 lecture videos. If you're unsure, you can go back to the lecture videos and see how the argument goes. Okay. Are there any questions in this problem? Yeah, I think there are no questions. We'll move to the next problem. This is a very straightforward one. So you have water at 15 degrees Celsius going over a flat plate with a velocity of 3 meters per second. Estimate the mass flow rate across the boundary layer at a distance of 5 centimeters from the leading edge of the plate. So I'm not asking you to find velocity, temperature, heat transfer, spin friction, any of this. I'm asking you to find the mass flow rate. So how do you go about this? How do you go about solving this? Can I simply write it as rho infinity times delta? Because I know that boundary layer thickness is delta, and I know the density because water and temperature are given. It's what, like let's say 1000 kilogram per cube. Velocity is given, and I said the distance is 5 centimeters. So if I take 5 centimeters, then all I have to do is get the mass flow rate is rho times area times velocity. Let's assume unit width of the plate. For a unit width of the plate, so this will be rho u infinity times delta. And in order to calculate delta, what we have to do? Yeah, we already know the correlation. Delta is 4.64 by Rex to the power half. We can calculate Rex because we know density, viscosity, everything for water. We substitute that, get Rex, and then calculate the delta, and then just do rho infinity delta. So, so is that correct, or are there any questions regarding that? If you recall, sometime back we were discussing something called the concept of, again, first is if you check it is laminar by boundary layer theory is valid or not, which you can directly compute the Reynolds number and see whether it is less than 10 power 5. But then the most important thing here is we discuss something called displacement thickness. We observe this that whenever you have the boundary layer, there is the velocity is not constant. There is a gradient, velocity gradient close to the wall. So there is some mass deficit. So in order to compensate for that, you define something called the displacement thickness. So the mass flow rate would actually be a little higher, the little lower if you just do rho infinity times b, rho infinity times delta. You have to add the displacement thickness to get the same mass flow rate. So the first step is to calculate, understand the concept of displacement thickness, compute the displacement thickness, and then add that to the value that we said just before, that rho infinity times delta plus this particular delta star. Then you will get the total mass flux, right? Okay. So we'll go step by step. The first one is checking whether the laminar boundary layer theory is correct in this particular case. So you take the water properties and then calculate the Reynolds number. Again, you calculate the Reynolds number at the leading edge. So if at the leading edge, if it is laminar, then it is laminar throughout because Reynolds number increases with x. So I'm getting around 10 power 5, so which is less than the critical number for transition, which is 5 into 10 power 5. So laminar boundary layer theory is valid. The next step is again just a recollection of what displacement thickness is. This is the distance by which the external potential flow has to be displaced outwards as a consequence of a decrease in the velocity in the boundary layer. So now you have to compute rho infinity times delta star and delta to be able to calculate the total mass flux. And the delta star is defined as 0 to delta 1 minus u by infinity dy. Now in this particular scenario, we will use the integral solution to solve for delta star. We know u by u infinity from the integral solution as 3 by 2 y by delta minus y by delta whole cube times half. So you substitute that into the integration and then you will get delta star as 3 by 8 delta. Now I have delta star. I already know delta from the integral solution. So I'll substitute those values to get delta star. So you can see how less this value is. So this is in meters. So this is like 0.6 mm and this is like 0.2 mm. So now I have delta and delta star. I can calculate my mass flow rate as rho infinite times delta plus delta star. That is coming to around 2.64 kg per meter second. Maybe it's not millisecond. Kg per second times meter. That meter is basically for the unit width of the plate. Are there any questions? Okay, I guess there are no questions. Then we move on to the next problem. This problem I would like you to solve. So we have a liquid film of constant thickness B and temperature T naught that is flowing in a steady laminar motion down an inclined solid surface under gravity at x equal to 0, which is say here. Let's say this is our horizon. A step change in the surface temperature from T naught to TW occurs. Determine the local heat flux if delta T is very much less than the thickness, which is B. Assume cubic temperature profile. I have not told anything about what profile you have to assume for velocity. So maybe I'll wait for some more time because this requires a little bit more solving. So I'll wait for say 5 minutes, and then you can go. You can try to. The first step is again to determine the velocity profile. So the procedure is straightforward. First, you have to find the velocity profile. Once you know the velocity profile, here the boundary layer thickness is not a problem because it is said that it is a constant thickness of B. So delta is already known. The unknown here is the velocity profile. Delta is not a function of x. We are saying it is constant and that is equal to B. So the one unknown from the momentum integral equation is kind of gone here. So the unknown is now the velocity profile itself. That is the first thing that you have to find. The second thing is I'm assuming cubic temperature profile, so which is again same as before. So you have to find the constants using the boundary conditions. Once you have that, you have to substitute that in the integral equation, energy integral equation, and solve for delta T. Once I have delta T as a function of x, then I'll be able to compute the local heat transfer, local heat flux, the heat transfer coefficient Hx, or local heat flux, whatever it is, Hx and Ux, whatever. All the other terms can be calculated once I know delta T. So maybe I'll give you like say 5 minutes to solve for velocity profile. Yeah, and then we'll see about the other ones. So are you able to solve for the velocity profile? Okay, so how do we go about solving these kind of problems? You start with, again, the same differential form first. So we will take the momentum equation. So now I have my momentum equation as follows, x momentum equation. So I'll have g sine theta term additional here. So the pressure term is not there because here there is no pressure gradient imposed. Essentially, it is again a flat plate, so we don't have anything of that sort. So this is my governing equation. Now we are assuming something that the initial forces are negligible, that the u and v, that this thickness is very small. I should be changing. I think this kind of got carried everywhere. So if I assume that, so basically, or put in another words, all we are saying is the driving force is the gravity, and this has achieved some kind of terminal velocity, which means whatever is the gravitational force is balanced by the viscous forces. So the viscous force is nu times v square dy square, and that is balanced by the gravitational term minus g sine theta. So if you take this equation, so my u will be this. So I have two unknowns to be determined. So my boundary conditions are at the wall at y equal to 0, I need u to be 0. And here, I do not know the upstream velocity, but I know that this has reached a constant profile. That the derivative at this, the del u del y at this free surface should be equal to 0. With those two boundary conditions, like I cannot put d square u dy square equal to 0 because I have this term. Theta is some finite quantity, g is some finite quantity, so I cannot use that particular boundary condition. So if I substitute these two conditions, the expression for velocity is given by this particular term here. So at y equal to 0, you have 0, and at y equal to b, you have the velocity to be. I think there was a mistake here. Yeah, I think there is a mistake here. So if you take this quantity out, so u of I is minus g sine theta by 2 nu y square. C1 is plus g sine theta b by nu times y. From this, if I take g sine theta b square by 2 nu, so that will leave me with a y by b here and minus. I've taken 2 out, so 2y by b minus y by b square. So this will be something like this. So at y equal to b, I have a finite quantity of velocity here, that is g sine theta b square, sorry, g sine theta by 2 nu. So that is basically the terminal velocity that you would obtain by balance of viscous and the gravity forces. Okay, now I have the velocity profile. Now we have to determine again the same temperature profile. I don't want to go much into the temperature profile because the boundary conditions are all very similar to what we derived before itself. So all these conditions are same. So if you substitute that, the expression you will be getting is very similar to whatever you got before. That will be 3 by 2 times theta minus 1 by 2 eta. So this is the same expression that you got even for a flat plate. So this I think is straightforward. Now we have to substitute this inside the energy integral equation and then solve for the, yes, then solve for delta T. So if I substitute inside the, okay, I think this got carried over everywhere. Just correct this. This is 2 minus y by b times this quantity, and then t minus t naught is this expression. If I substitute that into my energy integral equation, I can calculate del t del y from this. So t naught is a constant, so I can directly calculate del t del y as minus 3 by 2 times delta t. So this is the expression on the LHS. Now we'll calculate on the RHS. which is this term. Okay, there is 2 here. Okay, I think this 2 will get carried everywhere. So I have 2 times this, 2 times this, and 2 times this. The remaining terms are the same. So if I substitute delta t, so there will be a 2 here, there will be a 2 here, and I have 5, so I have another 2 here. The remaining terms are the same. So these 2 terms cancel each other. So I'll be left with 2 here, 2 here, a 2 here. So these 2 terms cancel each other. So have a 1 by 5 coming here, and then the remaining terms will here. Again, we'll use the assumption that delta t is very much less than b, in which case the cubic is much less than the square. So we will neglect the second term. So that will leave me, instead of 20, I'll have 10 here. Right? Now that I have the RHS and LHS, so I'll equate both the terms. So that will leave another 2 here. So this will give me an expression for delta T. Once I have the expression for delta T, how do I calculate the local heat flux? Yes, we already know how to calculate local heat flux, the minus K times delta del Y at Y equal to 0. And we already know the temperature profile. So if you substitute that, that will give me this particular term here. And we substitute the expression for delta T, 2 GB sine theta by 45 alpha nu. So as you can see, as X increases, the heat flux gradually decreases. This is the same thing that we observed in case of an isothermal plate. So as you go further and further, what happens is the temperature of the air or the stream keeps on increasing. So that would actually mean your net heat flux will actually decrease because the mean temperature close to that is keeps on increasing. So this is the local heat flux. Now, if you are asked to find the total heat transfer rate, all you have to do is integrate this particular expression within whatever limits of X that you have. Okay. Are there any questions in this? Yeah, if there are no questions, and this is the last problem I have for this week. These are the different kinds of model problems that you can have using the integral theory. So most of these problems will require you to assume a profile like we did here for temperature, or use some kind of approximation to get the velocity profile first, and then use another approximation for temperature profile. And both of these expressions will usually be in terms of delta, one unknown, the momentum, one unknown to be able to find from the momentum integral. That is the same that we have been doing in all these problems. So first you will assume a profile which will have one unknown variable which is delta, and we will find that unknown variable using the momentum integral equation. We do the same for temperature in terms of delta T, and we'll find the value of delta T using the energy integral equation. Once we have the expression for delta T, then the profile is actually a variable of is a function of delta T. So knowing this will give the value of the temperature profile. Once we know the temperature profile, we can calculate the heat flux using this expression. The same goes with the velocity boundary layer. First you have to find the delta. Once you have the delta from the momentum integral equation, you can substitute inside mu times del u del y at y equal to 0 and get the shear stress from that. So all these problems are in the same way. But now there are other extensions to the same problem, as in, for example, let's say the wall temperature here I've assumed it to be constant. But the temperature may not be constant. Or let's say if you assume uniform heat flux, you can solve the same problem assuming uniform heat flux. Then your temperature will vary as a function of square root of x. Yes. So TW will be T infinity plus some constant times root x, and then from that we have to find the value C, and then we will be able to solve the problem. But then these two are kind of extreme cases. But then in general, what could happen is the temperature, this surface can neither be constant heat flux nor be constant temperature. It will be having, say, different points having different temperatures. So this kind of things, scenario, consider a scenario where this is like a PV panel that is exposed to solar radiation, and let's say the conductivity is not that high for the particular material on the glass coating or the surface of the PV panel. Then what happens is the temperature distribution on the surface of the plate will be non-uniform. You might have to solve a conjugate heat transfer problem where you have to solve the convection, radiation, all of them simultaneously. Then the temperature distribution will be non-uniform, and then you cannot assume it to be uniform heat flux, or you cannot assume it to be uniform temperature. So which means then you have to assume a wall temperature profile also as some power series as C naught plus C1x plus C2x square plus C3x square x cube and so on. And then with that particular temperature profile, you should come back and solve these particular equations. But in order to, again, as I said, this can at most have one unknown variable. This particular method has only one energy equation, which means I can only find one unknown variable. So if I do not know anything in the x direction, then I will not be able to solve this problem at all. So in order to solve that, the x profile has to be given to me. So you have to do an experiment, measure the x profile, and then use this technique to determine the net heat flux. Right? Yeah. So these are the problems I have for this week. If you have any other further questions, then we can discuss. If not, we can call it a day for this week. Yeah, I guess there are no further questions, and we will call it a day for this week. We'll meet next week, the same time at 5 to 7, next Saturday. Next Saturday, we will solve some problems on nature convection. Or if you are interested, we can take up a problem of, say, variable temperature and then solve that one as well. So instead of having constant temperature or heat flux, we can consider a scenario where the temperature could actually be a function of x and y. And let's say if you are given the temperature profile in some form, then how do you be able to solve this? Or you can have scenarios where different sections of the plate have different temperatures which are known to you. Let's say you kept some thermocouples and measure the temperature values. In some way, you have an expression for temperature distribution on the surface, and how do you go about solving for the heat flux? Or you can also take up problems, other interesting cases where you have uh, a scenario where the Nusselt number correlation kind of changes along the plate. As the plate length keeps increasing, there will be certain regions which are laminar, certain regions which are turbulent, certain regions where delta T is less than delta, other regions where that particular value is greater than 1. So which means you have to use different correlations in different places. So in that kind of scenarios, how do you go about calculating the net heat flux? These are different kinds of variations of the problem that you can come across as you use this particular technique. So if any of you are interested, we can solve those problems as well next week. Yeah, I think there are no further questions, and we will end the session for today. Thank you for joining.